we go. Now we're live. So here we go. This should be fairly easy, I'm hoping. Today, 4/12/22. Our objective is to rationalize the denominator of a fraction. Okay? A lot of math words in there, and I'm going to explain what the words mean, okay? So, this is not a rational number. This is an irrational number. Okay? Pi is an irrational number. Okay? So any number that goes on and on and never repeats, any ugly decimal like this is an irrational number. So what we want to do, the square root of 3 is an irrational number. So to rationalize the denominator means we need to make the denominator, or the bottom of the fraction, become a normal or a whole or an integer or rational number. So to do that, if I go back to my chart, the trick is I want to be able to take the square root of it. Okay, so I look at my chart, and I know if I look at the chart I had from yesterday, look at my notes, and I want to make probably the square root of 3 into the square root of 9, right? I can make the square root of 3 into the square root of 9 because I know the square root of 3 is 3. So I'm going to multiply it by itself in a sense. So I like to say fix the problem with the problem. So I'm going to multiply by the square root of 3 over the square root of 3. I do the top and the bottom by the same number because that is the number 1. That's why you do top and bottom by the same, because in a sense I've multiplied it by 1, which does not change the value of my fraction. It just changes the way it looks. So top and bottom have to be the same number. So when I do that, I'll get 2 times the square root of 3 is 2 square roots of 3. I get the square root of 3 times the square root of 3, which is the square root of 9. And my whole purpose and goal was to get to here, right here, because I know the square root of 9 is just 3.
Mr. David, why
Yes.
don't you just write the equation as 2 divided by the square root of 3?
Yeah, great question. And you'll find that there will be some of your professors in college that will accept it, right? Absolutely. There'll be some that don't like that, and I don't want to be the one where you go to college and say, my math teacher never taught me that, okay? Right? Yeah. Anyway, there it is. Now, don't divide these 3's. Don't divide 3 into 3, because that is not really 3. That is really that number there, square root of 3. So you can't divide 3 into the square root of 3 because this is not a 3. This is that ugly decimal irrational number, okay? So you're done. We have the exact same value, except for the bottom of the fraction doesn't have a square root, okay? Same exact value, but the bottom does not have a square root, okay? Okay, now number 2 is a little bit different because you're going to have a cube root of 3 over the cube root of 5. And because it's a cube root, you need to make a perfect cube. So I need to make a perfect cube, and I have those in my notes. And I can probably make it into 125, right? 125 is a perfect cube. So to make it into 125, I'm just going to multiply it by the cube root of 25 times the cube root of 25, which is really 5 times 5 times 5. That actually makes sense, doesn't it? 5 times 5 times 5. Cube root of 5 times 5 times 5 is 5. So I get the cube root of 125, which is a perfect cube, over the cube root of 75. Cube root of 125 is a perfect cube root. 5 times 5 times 5, or the cube root of 125 is just 5. It's just 5. It's a nice rational number. And the cube root of 75 is not a nice number. It's an irrational number, but it's on the top. So we don't care. Okay, so same thing. I've got then the cube root of 75. I would rather keep that number instead of that number. Yeah, Giselle?
Never mind.
Okay. Now it's tempting to want to divide those, isn't it? 5 into 75, but that's really not a 75. It's really that number there. 5 doesn't divide into 4.2 and 7 does it. So you're done. So Michael, I agree with you. It seems silly. To me, either answer, in fact, this one actually even looks better, doesn't it? But the rule is, and it depends on what math teacher you get in college, Mr. Massey might expect this too, that you shouldn't have a root in the denominator. Okay. Okay, now example 3 is just a bigger version. Before I do anything though, let's rewrite it as 2 parts. I'm going to go the square root of 48 square root of x cubed over the square root of 20. Okay. Well, I just have to break things down first. So let's reduce it first. So before we do anything, let's reduce, because if we can reduce, it makes it easier. Okay. So I'm going to reduce this. I know 48 as a perfect square. I'm looking for a perfect square. It can be square root of 16 times the square root of 3. 16 is 48 is 16 times 3, and 16 is my perfect square. Okay. I want to take half of this, but I can't take half of it if it's an odd number. So I'm going to change that to the square root of x squared times the square root of x. Okay. In the denominator, 20, I'm going to reduce that to the square root of 4 times the square root of 5, because the square root of 4 is a perfect square. Okay, now, I haven't done anything with the denominator yet. I'm just reducing. That's what we did yesterday, right? Okay, so bit by bit, I know the square root of 16 is 4. I'm going to take half of my exponent and make that an x. The 3 and the x, we can't take the square root of either one of those, so they just stay a square root of 3x. In the denominator, I can take the square root of 4 and make it a 2 times the square root of 5. Now I'm not done. It's reduced, but I'm not done. So there's 2 things I can do. One, I can reduce 4 over 2 and make that a 2. You okay with that? So I'll do that first. I think I can reduce that to a 2, which is 4 over 2. But the second piece is I'm not supposed to have a square root in the bottom. So I'm going to make it into the square root of 25. So I multiply the square root of 5, square root of 5. I want to make it a perfect square. So if I multiply by the square root of 5 over the square root of 5, it will make it a perfect square, which is square root of 25, and I can take the square root of that. Okay, so let's see what I have. So in my denominator, I get the square root of 25. That was my goal, because then the square root of 25 is 5. All right, well, the denominator is rationalized. There's no square root. On the top, I reduce the 4 and the 2, so I'm going to get a 2x square roots of 15x. I can't do anything with that. 15 doesn't have any perfect squares in it. X is just x, so I'm going to rewrite it as 2x square roots of 15x. Again, it's tempting to want to divide the 5 into the 15. It's not a 15. Square root of 15 is this ugly number, and I don't want to really write that number, right? I'd rather not write that number. I'd rather write the square root of 15. Okay, how am I doing? Am I doing okay? Thumbs up. 1 thumb up. Any more? 2. Okay, 3. There we go. 4. Okay, let's turn the page. Okay, now these are the weird ones. These are the weird ones. So if you see a plus or a minus, multiplying by the square root of 5 won't do it. It won't do it. So we're going to multiply by what we call the conjugate. The conjugate is like the opposite. A plus square root of b or a minus the square root of b. Okay, the conjugate is just the opposite. Okay. So I'm going to multiply. So because I see a plus here, I'm going to multiply by the conjugate, which is going to be 4 minus the square root of 5. And I'll do the same thing on the top, 4 minus the square root of 5. So you have to do the top and bottom by the same thing, because that's the power of 1. That's the rule of 1. So this is really the rule of 1. Okay, let's see how this helps. So I'm going to distribute my numerator. 3 times 4 is 12. 3 times the negative square root of 5 is just going to be a negative 3 square roots of 5. Okay, whole number times square root is just going to be the 3 square roots of 5. On the bottom denominator, I'm going to FOIL it. 4 times 4. 4 times 4 is 16. 4 times a negative square root of 5 is a negative 4 square root of 5. Square root of 5 times a positive 4 is a positive 4 square root of 5. And finally, square root of 5 times square root of 5 is a negative square root of 25. Now, of course, when I get done, we'll look at it and say, wait a minute, all the square roots are going to drop out, aren't they? And that's our goal. That's our goal. So when we look at it, let you guys write this down. I'll pause for a minute, let you catch up. Our goal really is to get rid of the square roots. Well, these two will always cancel. That's why we do the conjugate. Always. And we'll always be able to take a square root here. That's why we do the conjugate, which is 5. Now, when I look at my problem, in the denominator, there are no longer any square roots. So, I'm going to have, in the bottom, 16 subtract 5 is 11. It's a whole number. And on the numerator, 12 minus 3 square roots of 5. Okay? And again, these two have the exact same numerical value. Again, Michael, I agree with you. Why do we need to do this? But somebody somewhere decided you couldn't have square roots in the bottom, okay? I agree with you. It's not hard to fix, though, is it?
Not as hard as it looks.
Well, it'd be easier just to leave it, wouldn't it?
Yeah.
I agree with that. Okay, now, how about example 5? Same thing, it's the conjugate, right? So we're going to do the conjugate again. I have a subtract here. So I'm going to multiply both the top and bottom by the same thing, and which is the conjugate? 5 plus 2 square roots of 2. And on the top, the numerator, 5 plus 2 square roots of 2. Okay? And then I'm going to have to FOIL. It's going to be a mess, but I can do it. It's going to be a bit of a mess, but I can do it. So, you ready? Am I going too fast? So let me multiply. Okay? 2 times 5 is 10. 2 times 2 times 2 square roots of 2 is going to be a positive 4 square roots of 2. 3 square roots of 2 times 5 is a positive 15 square roots of 2. And 2 times 3 is 6 times the square root of 4. Okay, I've just done the top or the numerator. Okay, I'm going to do the denominator here next. Okay. 5 times 5 is 25. 5 times 2 square roots of 2 is going to be a positive 10 square roots of 2. Negative 2 square roots of 2 times 5 is a negative 10 square roots of 2. And negative 2 square roots of 2 times a 2 square roots of 2 is a negative, my bad. Negative 4 square roots of 4, okay? So by doing that, by doing the conjugate, I think you can see that all of the square roots are going to disappear, right? That's the whole idea. These two cancel each other out, and the square root of 4 is 2. All of the square roots gone. Now there's some tidying up to do. We can tidy it up quite a bit. This is also going to be, square root of 4 is also a 2, right? So let's see what I have. In my numerator, I'll have a 10 plus 19 square root of 2 because I combined these two. They were the same. I added 4 square root of 2 plus 15 square root of 2 plus 6 times 2 is 12. In my denominator, I've got a 25 minus a 4 times 2, which is really an 8, right? Okay, last step. Let's get this to look decent. These are whole numbers. These are whole numbers. 10 plus 12 is 22. Plus 19 square root of 2. 25 minus 8 should be 17. And there it is. This is a great example of saying why do we need this silly rule, because it's a lot of work to get the same problem but in a different form, right? Okay. So I have a worksheet to follow this, and we've got time to get a lot of it done.